Hello and welcome. In the last video we looked at the force that was acting on the bottom of a pool, which we could represent by a horizontal thin plate. But what if our plate is vertical instead? Like what if we're talking about the side of a pool like we will in example 2? The problem is that the depth is not constant as you go across your whole plate, right? There's more pressure acting on the bottom of the plate and less pressure acting on the top of the plate. So we can't just do a straightforward calculation because depth is not constant. So what do? Well, what we're going to do is take that interval in the y direction. So the y direction is the one where the depth is changing, right? And we're going to cut it up into small pieces, small subintervals. And on each subinterval, we're going to assume that that's at a constant depth, each subinterval. So it's like we're taking our thin plate that's vertical, and we're chopping it up into strips, horizontal strips, where on each strip, the depth we can take to be constant. It's approximately a constant depth, and the more subintervals you use, the closer that approximation is true, the closer you are to having a constant depth for each strip. Let's draw a picture of example 2, which says what is the hydrostatic force acting on a 12-foot by 5-foot side of the pool described in example 1. What we're going to do is take that, we won't draw the 3D image of it again, we're going to take that side of the pool and put it in a 2D setting in an XY coordinate system. We'll make 12 feet along the x-axis and 5 feet along the y-axis. Draw the water. So we're just drawing like a kind of like a rectangle going out 12 from 0 to 12 in the x and 0 to 5 in the y. So that represents the side of the pool. And we're going to cut up the side of the pool into horizontal strips by taking that interval from y equals 0 to y equals 5 and dividing it up into a bunch of little subintervals. Now I'm not going to draw the subintervals, but you can imagine there are a whole bunch of little subintervals that we have from y equals 0 to y equals 5. And we'll just draw a sample strip of one of those subintervals. So we'll take the subinterval that's right there at like y sub I. Now these subintervals have a thickness, so these are delta y, just like normal, we have when we break into subintervals, we call the length of each subinterval delta x or delta y, and this is delta y in this case. And our goal is going to be just focus on that one thin strip, that one horizontal strip, and figure out what the force is that's acting on that strip. Now first we're going to figure out the pressure that's acting on the strip. By calculating rho GD. Now we're again in feet, so we're in the British units, so rho G is going to be 62.5 pounds per cubic foot. And now we have to figure out what the depth of that strip is. Well, the depth is going to be the distance, the vertical distance from the top of the water down to where the strip is. In this case, to figure that out, we'll take the top y value, which is 5, that's where the top of the water is at, minus the y value where the strip is at, which is y sub I. So over here we're going to write 5 minus y sub I. And this is in feet. I'll just write feet off to the side so we don't think it's part of the algebra there. Oops, let me write this with a blue close paren. Okay, so that would give us then 62.5 times 5 minus y sub I. And the units that we would have would be pounds per square foot. Now let's find the area of that horizontal strip. To get the area, well, we'll just take the length of that strip, which is always 12. Right? If we look at the side right here of the rectangle, that's always going to be out there at an x value of 12. And you could think in general it's going to be the x value here, which is 12, minus the x value on the left, which is 0, which is always going to be 12. 12 feet. I'll write the units at the end. Times the thickness, which is delta y. So this is 12 delta y, and the units are going to be square feet. Feet times feet is square feet. Then the force that's acting on just that little strip will be the pressure on that little strip times the area of that little strip. So we multiply p sub I times a sub I together, and the 12 times the 62.5 ends up giving you 750, and then you have 5 minus y sub I in parentheses, and then delta y. Now here the units of square feet cancel, and we just have units of pounds. Units of force, which are pounds in this case. Now that's just the force that's acting on that little strip. But then we have the force acting on all the other strips at all the other different depths. So what we'll do to get the total force on the strip is add up the forces acting on the little strips from I equals 1 to n, so the sum from as I goes from 1 to n of f sub I. And then to make that the exact force acting on the whole side of the swimming pool, we'll take the limit as n approaches infinity. So we go from our approximation to the true force acting on the side of the pool. So here we'll have the limit, so here we're going to have, I'll write it out, the limit as n approaches infinity of the sum as I goes from 1 to infinity of 750 times 5 minus y sub I times delta y. This is the Riemann sum. If it ever asks for a Riemann sum, this is our Riemann sum. And this then becomes, by definition, the integral. Here we have the integral across our y values from 0 to 5 of 750 times 5 minus y dy. And I'll just put a little dot 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 here and say when you finish that integral you get 9,375 pounds. That's a 5. Okay, so that's the total number of pounds acting on the side of that swimming pool. Thank you for watching, and see you in the next part.